Good day, students. Today we shall look into a new topic, that is Fresnel diffraction. Now, diffraction was explained as the bending of light over opaque objects or through slits, and light is encroaching into the shadow region. Okay. Now, this was basically explained using two principles: Huygens principle of secondary wavelets and the principle of interference. Now, in this figure, we can see that according to Huygens principle of secondary wavelets, if this line shows the initial wavefront, each point on the initial wavefront will act as a source of secondary wavelets. Okay, so we have spherical wavelets, secondary wavelets, and after time t, the tangent over all these secondary wavelets drawn will form the next wavefront. Okay. Now, when these secondary wavelets are formed, each of these wavelets happen to interfere with each other. And hence, here comes the principle of interference. So, when these two principles are taken into essence, we can explain diffraction. Now, diffraction is of two types: Fraunhofer diffraction and Fresnel diffraction. Fraunhofer diffraction is obtained when light source is assumed to be at infinity and the screen upon which the pattern is recorded is assumed to be at infinity. So the wavefronts should be almost planar. In the lab, this is achieved by making use of lenses. Okay. Now, since the Fraunhofer diffraction is a far field effect, the pattern obtained is as such. Okay. So at the central point, we have the maxima, and surrounding that we have the secondary maximas and minimas. Whereas Fresnel diffraction is a near field effect. Okay, the source will be kept nearer to the slit and the screen will also be kept nearer to the slit, and the wavefronts emerging will be, depending on the slit, it may be either spherical or cylindrical. And based on that, the diffraction pattern on the screen will be of this pattern. At the center, we can observe that we have a maxima, but surrounding the central maxima, we have a minima and other secondary maximas whose amplitude is greater than that of the central maxima. Okay, so in the near field effect, we have the diffraction pattern of this nature. Let us try to understand this using a video. Surrounding regions, okay, see, in the surrounding regions, the amplitude is greater, but as we move the screen away, farther, the central point becomes higher in intensity than the surrounding points. So this is the far field effect. Again, the video is started. We have the near field effect here. Going on to the far field effect. Let us see the video again. It will be starting here. See, near field effect. Going on to the far field effect now. Okay. So basically, there are two types of diffraction: Fraunhofer diffraction and Fresnel diffraction, and this picture shows the nature of the pattern. So as we move away from the slit, far from the slit, the diffraction pattern is of this nature, and if we move towards the slit, closer to the slit, the diffraction pattern will be of this nature. Okay. Now let us see in particular Fresnel diffraction. This figure shows the diffraction pattern. So at the center we have this region of low intensity, okay, and surrounding it we have regions of higher intensities followed by certain minima. At exact center, if you look properly, you will be able to see a very small bright spot, and this is called the Arago bright spot or Poisson spot. Now, to explain Fresnel diffraction, Augustin Fresnel made a few assumptions. Let's go through that. So, during Fresnel diffraction, the interacting wavefronts will be either spherical or cylindrical. Let us see a spherical wavefront of this nature. And it is at a distance of small a from the source and at a distance of small b from the screen. The optic axis is shown by the line SP, and the center of the screen is P. Now we draw lines towards the spherical surface at particular distances. We draw lines as shown here, and with these lines we draw a circle on the wavefront. These lines have particular distances. They are, the first line is at a distance of b plus half wavelength. Okay, so an additional path of half wavelength is taken, and at that distance we draw a circle. With next line is drawn at b plus twice half wavelength. Third line is drawn at b plus thrice half wavelength. Fourth line is drawn as b plus 4 times half wavelength. Likewise, till the end of the spherical wavefront, we draw the lines, and the last line can be assumed to be at a length of b plus n times half wavelength. Okay. Drawing a circle using these lines, we will be able to get the first circle. It is called the first half period zone. And using the second line, we get the second half period zone. The region between these two lines is called the, this annular ring will be the second half period zone. Now, this zone, the region between the the second circle and the third circle will be the third half period zone. And this region between the third half period zone and the fourth line will be the fourth half period zone. Likewise, we draw circles. And the last zone will be the nth half period zone. Now, these zones are called half period zones because the period in these zones will be having a phase of pi by 2. Right? Now, if we take the initial phase at the center to be 0, the phase at this point b plus lambda by 2 will be, it has a path difference of lambda by 2. Okay, this implies a phase difference of pi. Hence, if we take the average phase here, average period here, it will be 0 plus pi by 2, that is pi by 2. So its period is half, and hence these regions are called half period zones. It will be likewise in all these zones. Now the third assumption is the secondary waves from different zones combine to produce a resultant at each point on the screen. So let us take a point P on the screen. Now at P we get the amplitudes from, or the waves from, first half period zone, second half period zone, third half period zone. All these half period zones are contributing towards the amplitude at P. Okay. Now, the fourth assumption is that the resultant at each point on the screen will depend on B, the distance B, and inclination factor 1 plus cos theta. Theta is the angle between the optic axis and the normal drawn for each zone. Okay, so for the first half period zone, if we draw a normal to that zone, okay, the angle between that normal and the optic axis will be 0. Okay, so here the inclination factor will be 1 plus cos 0, that is 2. It will be having the maximum value. Now at the nth zone, the normal at the nth half period zone will be almost perpendicular to the optic axis, and hence the inclination factor will be 1 plus cos 90, that is 0. So the inclination factor will be 1. So as we move away from the center of the wavefront, the inclination factor is decreasing. Now let us mathematically try to calculate the amplitude on the screen due to all of these half-period zones. For that, we need to calculate the radius of each half-period zone, the area of the half-period zones, the amplitudes from each half-period zone, and the resultant intensity at the screen. Let us calculate the area of the nth half-period zone in Fresnel diffraction. The radius of the first half-period zone that can be calculated as small r1 square. It is given from OM1 square from the figure. Okay, and that can be written in terms of Pythagoras theorem as b plus lambda by 2 the whole square minus b square, right? And on expanding it, we get b square plus lambda square by 4 plus lambda b minus b square. Here, taking this term and this term, cancelling it out, we get this to be approximately equal to lambda b. Here I am writing approximately equal to because I have taken the assumption that this term lambda square by 4 will be very small. Okay, lambda is in the range of nanometers. Okay, 10 raised to minus 9. Hence square will be 10 raised to minus 18. Hence this term can be neglected. Now the radius of the second half period zone, that is R2 square is equal to OM2 square. Okay, so we are calculating the radius. Again, from Pythagoras theorem, I can write b plus 2 lambda by 2 the whole square minus b square, that is equal to b square plus lambda square plus 2b lambda minus b square, and that is again approximately equal to 2b lambda. Therefore, the radius of the nth half period zone, it is obtained from Rn square is equal to, that is OMN square, that is equal to b plus n lambda by 2 the whole square minus b square. Okay, this is equal to b square plus n square lambda square by 4, then plus nb lambda minus b square, and this is approximately equal to nb lambda. Now let us calculate the area of the half period zones. Area of the first half period zone, that is A1, is equal to, since it is a circle, I can write pi r1 square, right? That is equal to pi OM1 square. It is pi into lambda b. Now, the area of the second half period zone, that is equal to A2, written as pi OM2 square minus the area of first half period zone, that is pi OM1 square. It can be written as pi of 2b lambda minus b lambda, that is equal to pi b lambda. Okay, thus the area of the nth half period zone will be equal to an giving pi OMN square minus pi OM n minus 1 square, that is equal to pi nb lambda minus pi n minus 1 b lambda, that is equal to pi b lambda. Yes. Hence, we can say that the radius of the half period zones are proportional to square root of n, right? Whereas the area of the half period zones is independent of n. Okay. Next, let us calculate the amplitude due to the nth half period zone. Okay, so the first half period zone will contribute an amplitude towards the screen. The second half period zone will contribute to the screen. The third will contribute to the screen. So let us try to calculate the amplitude from each zone. We have the inference that the amplitude represented as Rn from the nth half period zone, it is proportional to the area of the nth zone, nth half period zone, and the inclination factor of the nth zone, and inversely proportional to the mean distance of the nth zone. So for these, let us calculate the values of each of the terms here. The mean distance of the nth zone is calculated by taking the average between the neighboring two half period zones. So let us calculate that. Mean distance of nth zone is given as average half of the distance towards the nth zone and distance towards the n minus 1th zone. Okay, so from the figure we get that distance to the nth zone is b plus n lambda by 2 plus distance to the n minus 1th zone is b plus n minus 1 lambda by 2. Okay, so this can be rewritten as 1 by 2 of b plus n lambda by 2 plus b plus n lambda by 2 minus lambda by 2. Here we have two b terms and two n lambda by 2 terms, that is half of 2b plus 2n lambda by 2 minus lambda by 2. This is equal to b plus n lambda by 2 minus lambda by 4. That can be rewritten as b plus, taking lambda by 4 as a common factor, 2n minus 1 times lambda by 4. So the mean distance of the nth zone is calculated as this. Next, let us calculate the area of the nth zone without taking any approximations. The area of the nth half period zone is obtained as pi of OMN square minus pi of OM n minus 1 square. This is written as pi b plus n lambda by 2 the whole square minus b square. Okay, that is pi of OMN square minus pi. We have b plus n minus 1 lambda by 2 the whole square minus b square. Okay, so expanding this we can write, let's take pi common, pi of b square plus n square lambda square by 4 plus nb lambda minus b square minus b square minus n square lambda square by 4 minus lambda square by 4, then plus 2n lambda square by 4 minus nb lambda plus b lambda plus b square. Okay, so this is the expression that you get. Okay, so here many terms cancel out. That is, b square and minus b square cancel out. N square lambda square by 4 and minus of that term cancels out. Nb lambda and minus of that term cancels out. Here again we have minus b square and here b square. These terms cancels out. And thus we can take the remaining terms and write it as pi of, we have b lambda plus, then let's write this term, 2n lambda square by 4, then we have this term minus lambda square by 4. Okay, that is, we can rewrite it as pi into b lambda plus 2n minus 1 lambda square by 4. Again, we can take out the lambda term and hence we get pi lambda into b plus 2n minus 1 lambda by 4. Okay. Hence, we can write the expression for amplitude due to the nth zone, nth half period zone, Rn as Rn is proportional to area of the nth half period zone was obtained as pi lambda into b plus 2n minus 1 lambda by 4 into the inclination factor 1 plus cos of theta n. Theta is the angle towards the nth half period zone, and divided by mean distance of the nth half period zone, that is b plus 2n minus 1 lambda by 4. The terms on the numerator and denominator, they cancel out. Hence we can write the amplitude due to the nth half period zone Rn is proportional to pi lambda into 1 plus cos of theta n. Here we understand that as the order of the half period zone increases, as n increases, the inclination factor from that zone will decrease. That is, cos theta n will decrease, right? As n increases, cos theta n will decrease, the inclination factor will decrease, and hence the amplitude from that zone will decrease. Okay, so the amplitude from the first half period zone will be R1, and the amplitude from the second half period zone will be R2. R1 will be greater than R2. If R3 is the amplitude from the third half period zone, R2 will be greater than R3. Likewise, it will be greater than Rn. Okay. Now let us calculate the intensity formed on the screen. From the wavefront, we have a lot of half period zones, and the amplitudes from each zone were called as R1, R2, R3, etc., Rn. Okay. So the phases will be different for each half period zone. So let us calculate the phase of the first half period zone. The phase of the first half period zone, it will be the average of the phases on that zone. Okay. So at the center, the phase of the wave is 0, and at the edge, that is at the point b plus lambda by 2, the phase is pi, right? And the average at that of these phases is pi by 2. Hence, the phase of first half period zone is obtained as pi by 2. Likewise, the phase of the second half period zone can be calculated as the average of the phases, that is pi plus 2 pi by 2. That will be 3 pi by 2. Okay. For the second half period zone, at both the ends we have a point of b plus lambda by 2 and at the other end b plus 2 lambda by 2, right? So for b plus lambda by 2 its face is pi, and for b plus 2 lambda by 2 the face is 2 pi. That is how we calculate the phases. Now again the phase of all the other zones will be likewise. So the phase of the other zones, of all zones, let us write all zones, will be in the order pi by 2, then 3 pi by 2, then 5 pi by 2, then 7 pi by 2, etc. Okay. Hence, when all these amplitudes from the different zone add up, we have to take in account of their phases. The resultant amplitude R will be equal to R1 minus R2. Okay, so there is a phase reversal here, right? Then plus R3, then here again a phase reversal, minus R4, etc., plus or minus Rn. Okay, thus the now here we are going to take some substitutions. Now R2 can be rewritten as the average of R1 and R3. Okay, right? Because its amplitude is well greater than R3, but it is less than R1. So we can write it as the average of R1 and R3. Likewise, R4 can be written as the average of R3 and R5. Okay, now substituting these terms in this expression for R, I can write another substitution is for R1. R1 is going to be written as R1 by 2 plus R1 by 2. Okay, so this is R1. And then for R2, I'm going to substitute R1 by 2 minus R3 by 2. The minus term is distributed, minus sign is distributed. Then R3 is written as R3 by 2 plus R3 by 2. Okay. Then the next term R4 is written as minus R3 by 2 minus R5 by 2. Okay. Likewise it goes on. Okay. Now what happens is, if you look at these terms, R1 by 2 can cancel out, minus R1 by 2. Minus R3 by 2 can cancel out this term. Again, these two terms cancel out. Likewise, R5 will be cancelled by the neighboring term. Okay. And finally, the remaining term will be plus or minus Rn by 2. Hence, the resultant amplitude can be written as resultant amplitude R is equal to R1 by 2 plus or minus Rn by 2. Okay. Now, if n is very large, the number of orders is very large, Rn will be very, very, very small. Thus, we get R to be approximately equal to R1 by 2. So, the amplitude on the screen is majority, check. So, the amplitude on the screen is mainly due to the amplitude from the first half period zone. Now, we actually see the intensity of light, right? So, let us write the intensity on the screen, I, it is proportional to R square, hence it is proportional to R1 square by 4. intensity is proportional to amplitude due to the first half period zone square by 4. Okay. Now, if there was any obstacle, very small obstacle, that is the size of R1, it will affect the diffraction pattern on the screen. Okay. So if I was conducting a Fresnel diffraction experiment, and if there was a tiny stone or a tiny paper at the central spot of that slit, I didn't know about it. On the screen, we won't be able to get any pattern. That is, in place of the first half period zone, in place of that R1, I have any obstacle that is preventing light to pass through it. We won't have any amplitude from the first half period zone, and hence we won't get any intensity pattern on the screen. So the obstacle size of R12 will affect the intensity on the screen. If there is an obstacle of size R1 by 2, that will affect the intensity on the screen. Okay, so this is the inference that we get. That's all for today's session. Thank you.